Summary: Subnetting and creating custom subnet masks. Now there are two ways to use this section. One is a general review if you've already gone through the previous sections, and the other one is a review session for knowledgeable technicians. Now if you've gone through this and all this makes sense, well, you're pretty much ready to start IP addressing and setting up your networks. If there are parts of this presentation that are a little bit fuzzy, I encourage you to go back to the previous sections for a detailed explanation of them.
Let's quickly review what a subnet mask is. Now remember, a subnet mask is an address that accompanies an IP address and indicates which portion of the IP address is the network ID and which portion is the host ID. Now the IP address and subnet mask are interrelated, and each only has meaning in the context of the other, and that the IP address and the subnet mask are the minimum address requirements for any TCP/IP device. One of the easiest ways to understand a subnet mask is to view it in binary. Now, ones in the subnet mask indicate which portion of the associated IP address is the network ID, and the zeros in the subnet mask indicate which portion of the associated IP address is the host ID. Now, for example, I have the address 207.23.106.99. Now, we know that this is a Class C address because the first number, 207, is in the Class C range. Now, the subnet mask, therefore, would be set to all ones in the first octet because the first octet is part of the network ID, all ones in the second octet because, again, the second octet is part of the network ID. The third octet also would be set to all ones because, according to Class C specification, the entire first three octets are the network ID. And then finally, the last octet would be set to ones to indicate that that portion of the associated IP address is the host ID. Now, when we convert these binary numbers to decimal numbers, the subnet mask would be 255.255.255.0.
One key piece of terminology we must be familiar with is, what is a physical segment? Now, a physical segment can be thought of a broadcast domain. Now, when we talk about a broadcast domain, we're talking about a portion of the network or all devices that can exchange information using a broadcast packet. Now, if two devices are separated by a repeater, a bridge, or a switch, they are considered in the same broadcast domain because these devices will forward broadcasts. However, if we have a router will not forward broadcast, and they really define our physical segments. So our definition of what is a physical segment, well, it's everything out one port of a router or between two routers, and that's again because a router does not forward a broadcast. Now this is important because of our IP addressing rules. Remember, all devices on the same physical segment share a common network ID. So that means all devices out one port of a router or between two routers would be on the same physical segment, and therefore they would have the very same network ID. Now of course they'll have a unique host ID to give them a unique IP address, but they all share a common network ID. Also, each physical segment has a unique network ID. So if we have a router with 3 different ports, that would give us 3 physical segments, and each physical segment would have a unique network ID, keeping in mind that all devices on each of those physical segments would share the common network ID for that physical segment.
Now remember, according to our classful naming scheme, that the address class also specifies the number of hosts we can support. Now Class A gives us a very large network with almost 17 million hosts. A Class B network, still a very large network at about 65,000 hosts, and a Class C network, essentially a smaller network with a maximum of 254 hosts. And when it comes to addressing our network, say we've been assigned the number 152.77.00. Now this is a Class B address, and I've listed out the subnet mask here, 255.255.00. Now this subnet mask, of course, it indicates the first 2 octets are the network ID, and the last 2 octets are the host ID. Now remember, one of the key rules of IP addressing is that all devices or all hosts on the same physical segment must have the same network ID as specified by this subnet mask. Now, according to the subnet mask, we have a single network ID, and if we only have one network ID, that would only allow us one physical segment. And with a Class B address, that's 65,000 hosts on one physical segment. As we saw in the previous slide, the Class B address 152.77.0.0 with the default subnet mask of 255.255.0.0 only gives me one network ID, and that would require me to only use one physical segment. But the truth is I'm going to have in a large network many physical segments, because remember, whenever I introduce a router, I create a new physical segment, because our definition of a physical segment is all devices out one port of a router or all the devices between two routers. Now, in order to correctly address the physical segments, we're going to have to use a custom subnet mask. Now, the custom subnet mask allows us to do this because the custom subnet mask allows us to create subnets. Custom subnet masks allow us to create these things called subnets. Now, a subnet is a portion or a subdivision of the IP addresses that are associated with a larger network ID. Now, the range of IP addresses, or the number of IP addresses in a subnet, is determined by the subnet mask. And we'll see that different subnet masks create different ranges of IP addresses. Now, when we start numbering our addresses, the subnets and the associated physical segments must be meticulously numbered, otherwise network communication will not be successful. To properly address our IP networks, we'll need to create a separate subnet or range of IP addresses for each physical segment. Now, we will specify these different subnets or range of IP addresses with a subnet ID. Now, I'm starting with a Class B address, the 152.77.00. Now, the default subnet mask, of course, because it's Class B, is 255.255.00. The 255 is indicating the portion of the IP address that is the network ID, and the 0 is indicating the portion of the accompanying IP address that is the host ID. Now, according to this Class B network and the associated subnet mask, I have one network ID, and I could support 2 octets of hosts, which is about 65,000 hosts. But what I want to do is create subnet IDs to number my physical segments. So what I'm going to do is, in a sense, steal or take some of the bits normally reserved for host addresses and turn them into subnet IDs, or use them as part of my subnet mask. When using custom subnet mask, we set up our subnet IDs like this. Now, all hosts or device will share the same network ID. Now, in our example, our network ID is 152.77. Now, all physical segments, all hosts will start with that because that's assigned to our entire network. Now then, each physical segment of the network would have a unique subnet ID, and then all computers on that physical segment would share that same subnet ID. Now then, of course, each host would have to have a unique host address, and that's unique to the subnet ID. When we're addressing our IP networks, we have to really be aware of the connection between the hardware and the software. Now, when I talk about hardware, I'm talking about the physical segments. Now, remember, physical segments are defined by routers, and our definition was all devices out one port of a router is considered a physical segment, or all devices between two routers is also considered a physical segment. So the hardware is the physical setup of the network. But now the software is the IP addressing, or the subnets, because remember, a subnet is the portion or a subdivision of the IP addresses that are associated with an assigned network ID. And the payoff here is that all hosts or all devices on the same physical segment have IP addresses in the same subnet. There are essentially 4 steps to custom subnetting. The first step is to design the physical network. Now, in many cases, the physical network may be already designed for us, and what we need to do is determine, first, the number of physical segments on the network. Then second, we have to figure out the maximum number of hosts on each physical segment. Now, step 2 is to choose a subnet mask, actually a custom subnet mask, that creates a number of subnet IDs that is greater than or equal to the number of physical segments, and also the subnet mask, the custom subnet mask, must give us a number of host IDs on each physical segment that is greater than or equal to the actual number of hosts on each physical segment, because we always have to match the software, that is the numbering of the IP addresses, to the physical segments. Then, step 3, we have to determine and number our subnet IDs, because they will be used when we sit down and number the actual host addresses. The first step of custom subnetting is always to design or assess the physical network. Now, there are many design issues as far as the network traffic, the geographic locations, the hardware and software limitations that may come into play, and really designing a network is outside the scope of this course. But from an IP addressing perspective, what we need to do is to assess the network and determine the number of physical segments on the network, and also determine the maximum number of hosts on any physical segment, because that will directly impact how we set up our IP addresses, because IP addressing really starts after the physical network is in place. Step 2, determining the proper subnet mask. Now, we've said that our physical network has 5 physical segments and about 5,000 hosts on each physical segment. Now we have to choose a custom subnet mask that gives us a number of subnet IDs that is greater than or equal to the number of physical segments, and also gives us enough host IDs that we have enough host IDs to number all the hosts on each physical segment. Now, we've been assigned the network address 152.77.0.0. Now, this is a Class B address, so the default subnet mask is 255.255.0.0. Now, when we convert that to binary again, the 255s turns into 8 ones. Now, remember, in a subnet mask, the ones indicate which portion of the associated IP address is the network ID and which is the host ID. So in our case, our default subnet mask, the first octet is 1s, second octet is 1s, because in a Class B address, the first 2 octets are automatically the network ID, and then the last 2 octets are the host ID, because the subnet mask, of course, is set to 0s. Now remember, our goal is to create subnet IDs for our physical segments, and we're going to create these subnet IDs by taking bits that are normally part of the host ID and turning them into part of the network ID, really what we're going to call the subnet ID. So now in this scenario, I've taken a single bit that's normally part of the host ID and said I'm going to set it aside to create these subnet IDs. Now, in this situation, with a single bit associated with subnet IDs, a single bit would give me the capability of creating 2 subnet IDs. The only problem with that, the original IP specification said that the subnet ID could not be all 0s or all 1s, so we always had to subtract 2 from the total number of subnet IDs. So with a single bit, we get 2 subnet IDs minus 2 subnet IDs. That gives us 0 subnet IDs. Now, therefore, that subnet mask, now if we do the conversion, if we take that third octet and convert it to a binary number, that converts to 128. That subnet mask would not be valid at this point. Now, one other calculation we have to be familiar with here, and that's the number of hosts per subnet ID. Now, just as I've added a bit to the subnet IDs, I've actually taken a bit away from the host IDs. Now, remember our binary calculation? The binary calculation says that if we have an octet, we have 256 addresses. If we have 2 octets, we'd have 256 times 256 addresses, which is the 65,000 and odd addresses. But what we've done here is we've actually taken a bit away from the host addresses, and whenever we take a bit away, we halve the number of host addresses. And so if we had 2 octets, we'd have the 65,000 addresses. Really, when we have a bit less than 2 octets, really 15 bits, we would have half the 65,000, or the 32,764 addresses. This is the chart we've developed. This is the subnet ID host chart for Class B network, and it specifies all the valid subnet masks we can use with a Class B network subnetting 1 octet, ranging from 1 bit to 8 bits, and it gives us the number of subnet IDs and the number of hosts per subnet ID. And then whenever confronted with a design problem, first we identify how many physical segments we have, how many hosts per physical segment, and then we look for a subnet mask, a custom subnet mask that gives us enough subnet IDs and gives us enough host IDs per subnet to match the physical network. Now this is a similar subnet ID host chart, but in this case it's for a Class A address. Now remember, in a Class A address, and I've listed one here, 33.0.0.0, the default subnet mask is 255.0.0.0, because in a Class A address only the first octet is the network ID and the last 3 octets are dedicated to host IDs. Now when we create a custom subnet mask, what we do is we start taking bits for the subnet ID from the second octet, and then the last 2 octets are dedicated to host IDs. Now when we follow through the chart here, we can see that, for instance, a subnet mask of this case of 224, now again that dedicates 3 bits to the subnet IDs, so that gives us 8 possible addresses. We throw out 2 for 6 possible addresses, but in the case of the host IDs, what happens is we have 2 full octets plus additional bits for host IDs. And so if we do the multiplication, we come out with over 2 million possible hosts per subnet. But a couple things to note. You can see going down the table that the number of subnet IDs as we add additional bits doubles. Likewise, or I should say in complete opposite, the number of host IDs halves going down the table, because again we're taking bits from the host IDs and giving them to the subnet IDs. But in the end the challenge is the same. If you're given a design scenario, first you determine how many physical segments there are and how many hosts on each physical segment, and then you'll choose a subnet mask, in this case a Class A subnet mask, that gives you the appropriate number of subnet IDs for the physical segments and gives you the appropriate number of host IDs per subnet ID to match the number of hosts per physical segment. Now here's the same chart for Class C networks. Now in this situation we've been assigned the Class C address 206.123.88.0. Now according to the specification, a Class C network has the first 3 octets dedicated to the network ID, and then the last octet is the host ID. So when we do subnetting, we do it on the 4th octet. Now if we were to look at the subnet mask of 224, we can see that again we've got 3 bits dedicated to subnet IDs, so the number of subnets IDs doesn't change because we still have 8 minus 2 or 6 subnets. But in the case of the host IDs per subnet ID, because we have a smaller portion than an octet, we certainly have a small number of hosts. In this case, since we have 5 bits dedicated to host IDs, that only gives us 32 minus 2 or 30 addresses. But again, this scenario is the same. Look at the physical network. Determine how many physical segments there are and how many hosts on each physical segment, and then choose a custom subnet mask that gives you the correct number of subnet IDs and host IDs per subnet. So if we were to choose a custom subnet mask of 224, our actual complete subnet mask would be 255.255.255.224, and we would use that on every computer on our network, and then it would be up to us administrators to hand out the actual IP addresses and default gateways. If we have a Class A address, our default subnet mask is always 255.0.0.0, and when we custom subnet on the second octet. So a custom subnet mask might be 255.248.0.0. Now in a Class B address, the first 2 octets are always the network ID. In this case, our example is 152.77.0.0. The default subnet mask is 255.255.0.0. So in a Class B, when we set up a custom subnet mask, we would put the custom number in the 3rd octet for a subnet mask like 255.255.2480. Now Class C says the first 3 octets are the network ID, so the default subnet mask is 255.255.255.0. So the custom portion of it would be in the 4th octet for a subnet mask that would appear like 255.255.255.248. In step 1, we designed or assess the physical network, and we determine the number of physical segments and the number of hosts on each physical segment. In step 2, we then chose a custom subnet mask that provided us with a number of subnet IDs that was greater than or equal to the number of physical segments, and also allowed us sufficient host IDs for each physical segment. Now in step 3, what we're going to do is we're going to actually number or determine the subnet IDs. Now remember, a subnet ID is a range of IP addresses that we will assign to the hosts on the same physical segment. And the way the numbering works is that, now again, all computers or all hosts on our network will share the same network ID. Each physical segment will have a subnet ID, and all the hosts on that physical segment will share not only the network ID but also the subnet ID, and then each host will have a unique host ID. Now each physical segment will have a unique subnet ID, and the range of IP addresses in each subnet will be determined by the subnet mask. And it's an important point to make that we just can't use any IP addresses when we set up our networks. When we do custom subnetting, we must meticulously number the networks in order for network communication to be successful. There is a short way to determine the subnet IDs for any custom subnet mask. Now again, in this situation, we're going to use the subnet mask of 255.255.224.0. We're going to focus in on the subnet ID portion, or the custom portion of the subnet mask, the 2240. Now when we convert that to binary, of course, that octet becomes 3 ones and 5 zeros. The way to determine the subnet ID is to look at the decimal conversion value of the farthest right 1 bit. Now in this case, the farthest right 1 bit is the 3rd bit. Now remember from binary math that the farthest left bit, the decimal conversion factor is 128, the next bit it's 64, the next bit it's 32. So our first subnet ID would be 32, or in this case 152.77.32.0. Then every subnet ID starts at a value or a multiple equal to the first subnet ID. So in our situation, the first subnet ID started at 32. Each subnet ID after that will start as a multiple of 32. So the next one is 64, next one is 32 added to that, 96, and on and on. Here's a chart where we've taken all the different custom subnet masks, and then we've listed out the subnet IDs associated with each custom subnet mask. And in each situation, what we've done to determine the subnet ID is to look at the farthest 1 bit in the subnet ID and convert that to its decimal equivalent. And we can see that the first subnet ID, now when we have a single bit dedicated to the subnet ID, the first subnet ID is 128. And then you can see that the numbers actually half. So the first subnet ID is 128, next one is 64, and they half all the way to 1. Now remember, if the first subnet ID starts at, for instance, 64, each successive subnet ID will also start at 64. Or if the first subnet ID starts at 8, each successive subnet ID will start at 8. Here we've taken two different charts and added them together. We started out with our subnet ID host chart for a Class B network, where we've listed the different custom subnet masks and then also listed the number of subnet IDs and the number of hosts per subnet ID that each custom subnet mask would give us. And then we've added the subnet ID information, listing out where the first subnet ID for each custom subnet mask starts and also the increment of each successive subnet ID. With this completed chart, you could take any network design problem and determine the correct custom subnet mask and also determine the subnet IDs that would be needed for each physical segment. Probably the easiest way to number your hosts or determine your host IDs is to first determine the subnet IDs. And I've listed out our subnet IDs from our example here. For subnet ID would be 152.77.00. We're going to throw that out. And the first one we can actually use is 152.77.32.0. Now remember, if the first one starts at 32, each next subnet ID will increment a multiple of 32. Now once we set up our subnet IDs, the first host is always essentially a 1 added to the subnet ID. So if the first subnet ID is 32.0, the first host is 32.1. If the next subnet ID is 64.0, the first host is 64.1. 96.0, first host 96.1. Now the last host always ends just before the next subnet begins. Now our scenario here, the subnet ID 32.0, the first host is 32.1, and it ends at 63.254 just before the next subnet ID starts at 64.1, and then that subnet ID goes all the way up to 152.77.95.254, ending just before the next subnet starts at 96.1.